मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
So, dear friends, now we are again going to start the remaining part of forging process. In this lecture, we will cover the forgeability and the hammers and presses that are different types of hammers and presses that are very common for forging, etc. So, we would cover these things. As you know that the most of the metalworking was done by hand in very beginning, that is until 30th century it was being done by hand, by hammering by a bigger hammer. At that time the tilt hammer was not developed and used primarily for forging bars and plates. The machine that time the machine used water power to raise a lever arm that had a hammering tool at one end. It was called that time a tilt hammer because the arm tilted as the hammering tool was raised. After raising the hammer, the blacksmith let it fall under the force of gravity and thus generating the forging blow. This relatively simple device remained in service for some centuries. Starting from 30th century, it remained same as it is described up to around few centuries. So, starting with this, we will cover the other types of machines, presses, hammers and all those things. But before that, let us see what is forgeability. We covered earlier also, but the forgeability concerns the metals and alloys that vary in forgeability from highly forgeable to relatively brittle one. So, relative forgeability is in fact an indicated, it is indicated value for metals and alloy used in open die forging basically. We would see that the table corresponding and we discuss in the earlier the forgeability of different alloys. Look at this figure number 1 where a schematic illustration of micro segregation in a large steel ingot is shown, because ingots are generally received from industry as a cast structure and that has to be forged or that has to be reduced to smaller size by forging operations. So, if you look at the structure, this shows the structure of a large steel ingot. You can see the shrinkage cavity, the segregation, the columnar structure, and then if you go back towards the center, the high segregation and center porosity are there, and then there is a negative segregation which is equiaxed structure, and this is what sedimentary oxide as well as inclusions and dendritic structure you can see there and all those things. So, that is how this structure is not suitable uh, direct part production, and once this kind of uh, cast structure, it has to be forced to reduce the cast structure into a better coarse grain structure or medium grain structure. Usually when one carries out the drying out forging operation on a given stock, while producing different shapes, common shapes in open dies, these are some of the examples, and one can see the steps also where the drying out forging stock is converted into in different shapes. One can see the upper one is the round billet, then once you dry it out to the slightly hexagonal one, and then further process and then further reduce in section, and then these are the other shapes, very common shapes, the hook shape and all those things. Another one there, the drying out forging of the stock from rectangular block, from rectangular raw material, so in steps and all those things, and there are few more very common shapes. These all shapes are produced by open die forging. So the open die forging, where we usually perform, if the workpiece as the raw material is smaller, by cold forging, and if it is bigger in size, we go for the hot forging. So this is just to show the things. So all the operations, as the drop hammer later came, but the uh, the blacksmith hammer is limited to the size of a forging. To overcome and to deal with the larger size of the forging and better stroke and higher forces on the forgings, there has been developed in different kind of hammers and presses for forging operations. So forging machines including, so forging machines can be classified according to their principle of operation. The hammers and high energy rate forging machines deform the workpiece by the kinetic energy of the hammer ram. They are therefore classed as energy restricted machines. The ability of mechanical presses to deform the work material is determined by the length of the press stroke and the available force at various stroke positions. Mechanical presses are therefore classified as stroke restricted machines. Hydraulic presses are termed force restricted machines because their ability to deform the material depends on the maximum force rating of the press. Although they are similar in construction to the mechanical and hydraulic presses, screw type presses are also classified as energy restricted machines. As far as the hammers are concerned, historically the hammers have been the most widely used type of equipment for forging. They are the best, expensive and most flexible type of forging equipment in the variety of forging operations they can perform. Hammers are capable of developing large forces and have short die contact times, and the main component of a hammer are a ram, a frame assembly, anvil and anvil cap, etc. The anvil is directly connected to the frame assembly. The upper die is attached to the ram and lower die is attached to the anvil cap. In operation, the workpiece is placed on the lower die. The ram moves downward, exerting a force on the anvil and causing the workpiece to deform. The forging hammers can be classified according to the method used to drive the ram downward. The various types of hammers are described. One can refer the different handbooks, uh, uh, but this table gives some of the hammers depending on the capacities, what capacities it deal with for the different types. For an example, if you look at the broad drop hammer, which is valid for around 45 to 34,000 kg of ram weight, and the number of blows that it can perform per minute, it is around 45 to 60. Like the another hammer which is air or steam lift hammer, that is around 225 to 7250 kg, and it can go up to the hammers per minute 60 blows. Similarly, there are electro hydraulic drop hammers and power drop hammers. So their blows number of, for an example, power drop hammer has got the number of blows per minute as 60 to 100. So that's a comparison of various types of forging hammers. One can select depending on the need of the forging, depending on the type of forging it is to be carried out. Another type of hammer, we call it as the gravity drop hammers. This slide shows the figure of such gravity drop hammer, one can see. So the gravity drop hammer consists of an anvil or base, supporting columns that contain the ram guides as it is shown here, and a device that return the ram to its starting position. The energy that deform the workpiece is derived from the downward drop of the ram. The height of the fall and the weight of the ram determines the force of the blow. The hammers have a falling weight, are rated size of around 180 to 4500 kg, that is up to around 400 to 10,000 pound almost. The standard size range from 450 to 1250 kg in increments of around 225 to 450 kg. The weight of fall of the ram varies with hammer size, and that ranges from about 900 mm for a 180 kg hammer to around 2 meter for a 3400 kg hammer. So this is the variation. So the gravity drop hammer one can select according to, this is what the different components of the gravity fall hammer one can see here, and there is a flywheel, and that gives the enough energy to such kind of hammer. The other hammer, as I mentioned in the table, it is the air lift gravity drop hammer. So this kind of hammer is similar to the broad drop hammer, in that the forging force is derived from the weight of the falling ram assembly and upper die. It differs in that the ram is the air lift hammer is raised by air or steam power. The stroke control dogs preset on a rocker and actuated by the ram. Control power to the ram cylinder. With the hammer shut down, the dogs can be reset on the rocker to adjust the stroke length. A device is available that allows both a long stroke and a short stroke in the variable sequence. The range of size generally available in airlift hammer is around 225 to 4500 kg. The weight of the forging that can be produced in an airlift hammer of a given size is about the same as that which can be produced in its broad drop hammer counterpart. The other hammer which comes is electro hydraulic gravity drop hammer, because in the recent year two significant innovations have been introduced in the hammer design. The first is the electro hydraulic gravity drop hammer. In this type of hammer, the ram is lifted with oil pressure against an air cushion. The compressed air slows the upstroke of the ram and contributes to its acceleration during the down stroke blow. Therefore, the electro hydraulic drop hammers also has a minor power hammer action. Power drop hammers, in a power drop hammer, as I said, the ram is accelerated during the down stroke by air stream. Or hydraulic pressure. The component of a steam or air actuated power drop hammer are shown here in figure number 2. One can see this equipment is used almost exclusively for closed die, that is the impression die forging. So, this is what the principal component of a power drop hammer with a foot control to regulate the force on the blow. One can see the different components. The top one is your safety column head, then the cylinders, then the cylinder head, and then the other things, and the annual the platform, the forging, the guides, and all those things one can see here. A common power drop hammer. Power drop hammers are very popular in forging of large forging components. The power drop hammers are in fact rated by the weight of the striking mass, not including the upper die. Hammer ratings range from 450 to 31,750 kg. The large mass of a power drop hammer is not apparent because a great deal of it is beneath the floor. A hammer rated at 22,700 kg will have a sectional steel annual block weighing around 4,53,600 kg or more. The ram, piston and piston rod will have an aggregate weight of approximately 20,400 kg. The striking velocity obtained by the downward pressure on the piston sometimes exceeds around 7.6 meter per second. So, the rating hammers by the weight of the striking mass is not correct, although it has been the common practice. The more realistic method of rating hammers is by the maximum energy in joules or foot pounds, or that the ram can impact to the hot metal during a single blow at a maximum energy setting of the hammer control. The usual energy supplied to the forged metal by the hammer ram depends on the hammer design, that includes your weight of the ram and the pressure on the drop of the piston, the ratio of the annual, the weight versus the ram weight, and the hammer foundation design. Although there are many advantages associated with the use of power drop hammers, the greater striking forces they develop give rise to several disadvantages as well, as much as 15 to 5%, and in hard finishing blow up to around 80% of the kinetic energy of the RAM is dissipated in the annual block and foundation, and therefore does not contribute to the deformation of the workpiece. The other class of hammer that we call it as the die forger hammer. The die forger hammer are similar in operation to power drop hammers, but have shorter stroke and more rapid striking rates. The ram is held at the top of the stroke by a constant constant source of pressurized air, which is admitted to and exhausted from the cylinder to energize the blow. The die forger hammer from the manufacturer are capable of delivering around 5.5 to 89.5 kilojoule of energy per blow, very large energy. The blow energy and the forging program, that is the number of the die station and the number of the intensity of the blow at each station, are in fact pre-programmed by an operator. There are other category of the hammer, we call it as the counter blow hammers. So the counter blow hammers, another variation of the power drop hammer, is widely used in European countries. In fact, these hammers develop striking force by the movement of the two rams simultaneously approaching from the opposite direction and meeting at a midway point. Some hammers are pneumatically or hydraulically actuated, others incorporate a mechanical hydraulic or a mechanical pneumatic system. The rams of a counter blow hammers are capable of striking repeated blows. They develop combined velocities of 5 to 6 meter per second. Horizontal counter blow hammers have two opposing die carrying rams that are moved horizontally by compressed air. Heated stock is positioned automatically at each die's impression by a preset pattern of accurately timed movement of a stroke of a stock rather handling device, and a 90-degree rotation of a stock can be programmed between the blows. This is what this figure number 3 shows, the principal component of a vertical column blow hammer with steam hydraulic actuating system. One can see here the upper ram, the lower ram, the workpiece holding the upper die, the lower die, then the steam return valve, the tie plate, the steam cylinder assembly, the steam for the forging stroke, the floor line, and then the piston rod, then the piston hydraulic fluids, that all shows. So it's a counter blow hammer which is operated by a steam hydraulic actuating system. Another very popular hammer, we call it as the double frame power hammer, which is very often used for open die forging. So we can say that the open die forging hammers. This figure shows one of such hammer. So open die forging hammers are made with either a single frame or that is often termed as C frame or single arc hammers, or a double frame often which is called as double arc hammers. This is what is shown, one of the double arc hammer. which is used to make a large percentage of open die forging. The rated side of the double frame open die forging hammers range from around 2700 to around 11,000 kg. Although large hammers have been built, a typical open die forging hammer is operated by steam or compressed air, usually at pressure of around 690 to 825 kilopascal for steam, and around 620 to 609 kg pascal for air. So these pressures are similar to those used for the power drop hammers. High energy rate forming machines are also there, that we call it as HERF, HERF machines. So that means it is a high energy rate the forging machines, where the high energy rate forging machines are essentially high speed hammers that utilizes. They can be grouped into three basic designs: the ram and the inner frame, the 2-ram and controlled energy blow type. Each differ from the others in engineering and operating features, but all are essentially very high velocity single blow hammers that require less moving weight than the conventional hammer to achieve the same impact energy per blow. Alright. So all the design employ in fact a counter blow principle to minimize foundation requirement and energy losses, and they all use insert high pressure gas controlled by a quick release mechanism for rapid acceleration of the ram. In none of the design is the machine frame which is required to restrict the forging force. The ram and inner frame machines are another category that are produced in several sizes, that is ranging from a capacity of 16 kg to around 750 kilojoule of impact energy in one strike. Such machines, which is illustrated here in figure number 5, has a frame which is consisting of two units. In inner are working, the frame is connected to a firing chamber, and an outer or guiding frame within which the inner frame is free to move vertically. As far as the applicability is concerned, the high energy rate forming machines are basically limited to fully symmetrical or concentric forging, such as wheels and gears or coining operations, in which little metal movement but high die force are required. Information on the HERF process, that is high energy rate forming processes, as well as the examples of the part forged using the high energy rate forming processes are available in the article. One can refer these articles on high energy rate forming in any textbook or the book we have already given in the references. One can see these three basic machines: the concept machine of the high energy rate forming, the A, B and C. One can see here the A is the ram and the inner frame machine, B is 2-ram as the machine, and C is the controlled energy flow machine. So the triggering and expansion of the gas in the firing chamber causes the upper and lower arm to move toward each other at high speed, and outer frame provides the guides surface for the ram. So one can see the differences in between the three. The 2-ram machines are also available in several sizes. The largest has a rating around 400 7 kilojoule of impact energy. In a 2 ram machine, the counter blow is achieved by means of an upper ram and a lower ram. An outer frame provides vertical guide for the 2 ram, vertical movement of the trigger points, that is a high pressure gas, to enter the lower chamber and the space beneath the driving piston, and therefore this force and the driving piston, that is rod, lower arm, lower ram and lower die upward. The reaction to this force drives the floating piston cylinder, upper ram and upper die downward. The rods provide relative guidance between the moving upper and lower assemblies. After the blow, hydraulic fluid enters the cylinder, returning the upper and the lower ram to their striking position. The gas is recompressed by the floating pistons, and the gas seals at the lower edge of the drive pistons are established. When the trigger is closed, the hydraulic pressure is released. The high pressure gas in the lower chamber expands through the drive piston ports and forces the floating piston up, and the machine is ready for the next blow therefore, and this cycle goes on again and again. In case of controlled energy flow forging machines, that is in two sizes are available, with rating as 99 and another as 542 kilojoule of the maximum impact energy. These machines, as shown in the figure C, are in fact counter blow machines from the standpoint of having separately adjustable gas cylinders and separate rams for the upper and lower dies. However, self reacting principles are not employed. The lower ram has a hydraulically actuated vertical adjustment cylinder, so that cylinder's stroke length may be preset. Another very important category of power striking machines are mechanical presses. So, the mechanical presses, almost all mechanical presses imply flywheel energy, which is transferred to the workpiece by a network of gears. Cracks, eccentrics are levers driven by an electric motor and controlled by means of an air clutch. Mechanical presses have a full eccentric type of drive shaft that impart a constant length stroke to a vertically operating ram. This is what is shown here in figure 6. Various mechanisms are used to translate the rotational motion of the eccentric shaft into linear motion to move the ram. The ram carries the drop, it carries the top or the moving die, while the bottom or stationary die is clamped to the die seat of the main frame. The ram stroke is shorter than that of a forging hammer of a hydraulic press. Ram speed is greatest at the center of the stroke, but force is greatest at the bottom of the stroke. The capacity of these forging presses are rated on the maximum force they can apply, and ranges from around 2.7 to 142 mega Newton, very heavy force. In detail, however, mechanical forging presses are considerably different from mechanical presses and are used for forming sheet, The principal differences are forging presses, particularly their side frame are built stronger than the presses for forming sheet metal. Forging presses deliver their maximum force within 3.2 mm of the end of the stroke, because maximum pressure is required to form the flash. The slide velocity is a in a forging press is faster than in a sheet metal deep drying press, because in forging it is desirable to strike the metal and retrieve the ram quickly to minimize the time the dies are in contact with the hot metal. As far as the advantage and limitations are concerned, uh, the comparing the hammer forging, mechanical presses, forging. So if you compare to the these results in a accurate close tolerances parts. So mechanical presses permit automatic feed and transfer mechanism to feed, pick up and move the part from one die to the next, and they have a higher production rate than the forging hammers. The stroke rate may vary from 30 to 100 stroke per minute, because the dies used with mechanical presses are subject to squeezing forces instead of impact forces. Harder die material can be used in order to extend the die life. Dies can also be less massive in mechanical press forging. One limitation of mechanical press is their high initial cost, approximately 3 times as much as the forging hammers that can do the same amount of work. Because the force of the stroke cannot be varied, mechanical presses are also not capable of performing as many preliminary operations as hammers. Generally, mechanical presses force the preform and final shape in 1, 2 or 3 blows. Hammers are capable of delivering up the 10 or more blows at the varying intensity. So that's the basic difference between the hammer and mechanical presses. This is what it shows the component of a mechanical forging press. Different two views are shown. One can see here, that's the bigger the motor and all those things one can see. As far as the principles of operation of mechanical press, which is driven by a pitman arm, it is shown here. That is a pitman arm means it is a connecting rod. This is shown here, and in figure 8 the principle of operation of a wedge driven press is shown here. So that's the connecting rod in the second case, the wedge, ram, table, worm gear and all those things. This figure shows the principle of operation of the mechanical press with a Scotch yoke drive. So there are 4 versions you can see. The number A is the arm is at the top of the stroke, the Scotch yoke is cantered. Second is the Scotch yoke is in the extreme forward position midway through a downward stroke, and in case of C it is at the bottom dead center. The Scotch yoke is in the center of the ram, and in case of D it is at midway through the upward stroke. The Scotch yoke is in the extreme rear position. So as a comparison of the capabilities of the forging presses, This table 2 gives the comparison of the capabilities of the mechanical press with those of the hydraulic and screw presses. So one can see the mechanical press, the force it is of the order of 2.2 to 142, and the hydraulic it is this one. The pressing speed varies from in case of mechanical 0.06 meter per second to 1.5 meter per second, and in the hydraulic presses it is 0.03 to 0.8. So this is what's the comparison of the forging presses, mechanical and hydraulic type. In fact, the hydraulic press, if you look at the component in this figure, for the 4-post hydraulic press for a closed die forging, these hydraulic press are used for both open die and closed die forging. The arm of a hydraulic press is driven by hydraulic cylinder and piston, which are part of a high pressure hydraulic or hydro pneumatic system. After a rapid approach speed, the ram with upper die moves at a slow speed while exerting a squeezing force on the work metal. Pressing speed can be accurately controlled to permit control of metal flow velocities. This is particularly advantageous in producing close tolerance forging. The principal component of these press is shown here. One can see the lifting cylinder, the stuffing box, the other columns, the very heavy duty columns and rams, crosshead, and then the lifting plungers and all those things. In fact, the advantages of this kind of hydraulic press includes that the pressure can be changed as desired at any point in the stroke by adjusting the pressure control valve. Secondly, the deformation rate can be controlled or varied during the stroke if required, and this is especially important when the forging metals that are susceptible to rupture at high deformation rate one can go for. The split dies can be used to make parts with such features as offset flanges, projections and back draft, which would be difficult or impossible to incorporate into hammer forgings. And another advantage with hydraulic presses that when excessive heat transfer from the hot workpiece to the dies is not a problem or can be eliminated. The gentle squeezing action of the hydraulic press result in lower maintenance costs and increase in die life because of less shock as compared to other type of forging equipments. And another advantage is that maximum press force can be limited to a for protecting the toolings as well. As far as the disadvantages are the hydraulic presses are concerned, there are 3 major points. Number 1, the initial cost of the hydraulic press is higher than that of an equivalent mechanical press. Secondly, the action of the hydraulic press is slower than that of the mechanical press, and thirdly, the slower action of the hydraulic press increases contact time between the dies and the workpiece. When the forging materials at high temperature such as nickel based alloy and titanium alloys, this results in shortened die life because of the heat transfer from the hot work metal to the dies. So this way we will further continue other types of presses like screw presses and all that, and then few more toolings and all those associated to forging cold and hot we will discuss in the next lecture. So thank you very much for listening carefully. Thank you.